Welcome again to the lectures on state space approach to control system analysis and design. We are learning LYPUNOV'S stability. In the last two lectures, we saw some mathematical foundation essential for learning the LYPUNOV'S stability. Then definitions of stability, asymptotic stability and instability in the sense of LYPUNOV and the LYPUNOV'S direct method. Now we continue, and the topic in this video is the application to linear and nonlinear systems. In fact, we are going to learn the indirect method because we found that there the choice of LYPUNOV function was something very difficult task. So we apply the concepts first to linear systems and then also to nonlinear system. So we are given with a linear system x dot equal to ax, and in this case it is very easy to choose a LYPUNOV function as a quadratic function x transpose Rx. This we also know that it is global, and we have also seen that stability of nonlinear systems is applied to the whole state space. It is global in the nature. So we choose a LYPUNOV function which is a quadratic form x transpose Rx. If we differentiate it, then we get v dot x, and this x transpose Rx becomes x dot transpose Rx, and x transpose R x dot. This is by chain rule. The differentiation of this gives this. Now in this we make a substitution. X dot is Ax, so x dot transpose is x transpose A transpose, and then Rx we bring as it is. Similarly, x transpose Rx dot, here again x dot we make a substitution as Ax. So we have x transpose R Ax. Now we separate out on the left x transpose and on the right x, and we are left with A transpose R plus Ra in between. So this expression reduces to this one, and there we denote A transpose R plus Ra with minus Q. So we define Q as negative of A transpose R plus Ra. Then this V dot X gets expressed as minus X transpose QX. Remember, as R was positive definite, and symmetric, we see Q will be symmetric, and we have to see further about it. Now what we see that this V dot X, if it is negative definite, then because Vx is positive definite, because of R being positive definite, so we have Vx positive definite, V0 0, it is quadratic form, it satisfies the conditions of being the LYPUNOV function. So Vx is a LYPUNOV function, and V dot, if it comes out to be negative, then the system will be stable, and for V dot X to be negative definite or negative semi-definite, Q must be positive definite, because it is the minus Q which is coming here, X transpose minus QX. So if Q is coming as positive semi-definite, then V dot X will be negative semi-definite, and that means the system will be stable. So to apply the LYPUNOV'S indirect method, what we have to do, we have to choose a positive semi-definite matrix Q, and we have to set up the equation A transpose R plus RA equal to minus Q, and we have to solve it for R. Thereafter, we have to check whether R is positive definite or not. If R is positive definite, then the system will be asymptotically stable, and if not, then it may be unstable. Now we apply that to this system, this second order system. x1 dot is x2 and x2 dot is kx1 minus 2x2. We have to find the condition of stability of this system. Now for this, Q has to be chosen little judiciously to result into ease of mathematical manipulation. We will see that why I am telling this point. But let us say we select this Q, which is Q11 is 2, rest all entries 0, and this is of course a positive semi-definite matrix. So with this Q, we set up the equation A transpose R plus RA equal to minus Q. In place of A transpose, we substitute transpose of this matrix. So 0, 1 comes along column and K minus 2 comes as other column. So this is A transpose, this is R. We have chosen R to be a symmetric matrix. You can see we have R12 at both these places. Then RA, this is R, this is A, which is equated to minus Q. And when we do the various manipulations and compare the terms on the left with those on the right, so that A transpose R plus RA, let me go back to the previous slide. A transpose R, this will be a 2 by 2 matrix. RA will be a 2 by 2 matrix, which will be transpose of this product. Then we sum, so we get a 2 by 2 matrix which contains R's in its various terms, R11, R12, etc. So the terms on the left are to be equated to respective terms on the right, and that will lead to these equations, these three equations. 2k R12 equal to minus 2, R11 plus k R22 minus 2 R12 equal to 0, and the third one 2 R12 minus 2 R22 equal to 0. Now first one will give R12 equal to minus 2 by 2k or minus 1 by k. This is here. In the second one, in the third one, we substitute R12 obtained from the first one. We get R22 as this, minus 1 by 2k. And that R12 and R22 we substitute in the second equation, we get R11 as this. So thereby we get the R matrix. This is a symmetric matrix because we started assuming it as a symmetric matrix. That is a necessary thing to be done. So now we have to check whether it is positive definite or not. So first thing is this term, which is R11, that should be greater than 0. And that leads to this, that half minus 2 by k should be greater than 0. And by simplifying we get k should be less than 4. Then other condition we get is that the determinant of this R should be greater than 0. That means we get this multiplied by this minus these two multiplied. So 1 by 2 minus 2 by k multiplying with minus 1 by 2k minus 1 by k square, which is product of this. Product of this is 1 by k square and minus because we are evaluating the determinant. So this should be greater than 0 for R should be are to be positive definite, and on simplifying we get this, and which gives this as further. So we get that if k is less than 4 and k is less than 0, these two conditions, then this R will be positive definite. And combining the two conditions, we get the condition that k should be less than 0 for R to be positive definite, and that means that for the stability of that given system, stability of this system, we should have k greater than 0 as is established by Lyapunov condition. Of course, you can cross check by some other method, maybe directly by obtaining the eigenvalues. Now we come to the nonlinear systems, the indirect method of Lyapunov to nonlinear systems. Here we don't have to choose in the beginning the Lyapunov function. We get to Lyapunov function indirectly. So what we do is, we have a given nonlinear system, and in general the nonlinear system stability is not global. It is in the neighborhood of equilibrium, and of course we are assuming the equilibrium to be the origin of the state space. So what we are concerned is, we want to find the largest region around the equilibrium or around the origin of the state space in which the nonlinear system will be stable. That is the situation for which we want to apply the Lyapunov's stability criterion, Lyapunov's stability method. So we consider this nonlinear system x dot equal to fx, and we expand fx using the Taylor series, and thus fx becomes f at x equal to 0 plus summation of partial derivatives of f with respect to different components in x, del f by del x1 plus del f by del x2, etc., all evaluated at the origin, plus the summation of the partial derivatives of second order, del 2f by del x1, del x1, del x2, etc., again evaluated at x equal to 0. So we can assume fx to be expanded using kind of Taylor series like this, and at x equal to 0, at the equilibrium point, we assume that f0 is 0. So this becomes 0, leaving all the other terms, which is reproduced here. We have first order partials evaluated at x equal to 0 and summed up together. We have second order partials, higher order partials, etc. And what we do is, we represent this, because this multiplying to x, this is the linear approximation to the nonlinear system. This is fx becomes ax, and this gx is collectively all the second order and higher order terms. They are brought in gx. So the given nonlinear system fx is approximated as a sum of a linear component and a nonlinear component. The nonlinear component is comprising of the Taylor series expansion of the function fx, the second order partial derivatives and other higher order partial derivatives taken together. So fx is approximated as ax plus gx, and because x dot was fx, x dot is fx, fx got approximated that way. So we have the system x dot equal to ax plus gx. Now this system which is rewritten here, x dot equal to ax plus gx, first we have to check the linear part. That means x dot equal to ax we can check first. And if this linear system is stable, then non-linear system will have assured region of stability around x equal to 0 or the equilibrium point. However, if this linear system itself comes out to be unstable, then non-linear system also will be unstable. So what we do is we consider the linear part of the dynamics first and we analyze it. And this was told in the previous part of this lecture. We have to choose a positive semi-definite matrix Q, and we have to set up this equation and we have to solve for the matrix R. We have to check this R should be positive definite for the stability of the linear part of the dynamics. If it is not, then as I told, the linear system will be unstable, linear part of the dynamics will be unstable, and so the nonlinear will anyway be unstable. So once we get a positive definite R, then we also get a Lyapunov function. This is the ease. I was telling earlier in this lecture that it is very difficult to choose to find out a good Lyapunov function, a good candidate which is a Lyapunov function. So through via the linear system, when we get R which is symmetric and positive definite, thus the linear system comes out to be stable, then we also get a Lyapunov function, a candidate for the nonlinear system. This quadratic is the Lyapunov function for the nonlinear system. And then what we do is we differentiate it to get V dot as x dot transpose Rx plus x transpose Rx dot. And in both the places we substitute, because x dot is Ax plus at Gx. So we will make this substitution in place of x dot at both the places. So this is the first one. X dot is Ax plus Gx. So x dot transpose will be x transpose A transpose plus G transpose X, and Rx as it is. Similarly, x transpose R into x dot gives this. And then we simplify it. We open the products and simplify, and that gives one this and other this. And we see that this is same as x transpose Qx, that Q we had selected. So this we substitute that, sorry, this is same as x transpose Qx with minus sign. So this we substitute. And this is scalar. Each one of them is separately a scalar. So it is 2 times one of them. So 2 times x transpose Rgx. So this V dot x gets expressed like this. And in that, now we have to check whether this V dot x is negative definite in a region around the equilibrium. So if it is less than 0 in a region around equilibrium, essentially we have to establish that region. We know that because the linear part of the dynamics was stable, there exists a small region. We have to determine that extent of the small region. We have to determine that, and that will give us the region of stability of the nonlinear system. We take a small example. Okay, before we go to example, so this essentially this x transpose Rx which is represented as Vx. So that Vx less equal to K, in which V dot X will be less than 0, has to be determined, and so we have to determine the K, the radius of the that sphere X transpose Rx. So and the surface Vx equal to K, in which V dot X will be negative, that K has to be determined, or in other words Vx and V dot should become tangent. At Vx equal to K should become tangent to V dot X equal to 0. So we have to find that K, and that will give the largest region over which the nonlinear system is stable. This will be the region. Vx less than equal to K will give that region. So now we take one example. Here we don't have to do Taylor series expansion. It is already given such that the linear and nonlinear components are visible. x1 dot is minus x1 plus 2x2, and x2 dot is minus 2x1 minus x2 plus x2 square. So this term is the nonlinear part. It is in the derivative of the second state. First state, there everything is linear. So together, of course, it is a nonlinear system because of that quadratic term. Now obviously, as I said, this is the linear dynamics which gives this A matrix, and this is the nonlinear dynamics, 0 here. So this 0 x2 square gives the nonlinear part gx. So we express this nonlinear system as ax plus gx, in which a is this and gx is this. And now we select a q and find out whether in X transpose Rx, by setting up that equation A transpose R plus RA equal to minus Q, we get R as positive definite. If yes, then the linear part of dynamics is going to be stable. So this is A transpose for the A given there. A is here, minus 1 2 minus 2 minus 1. So minus 1 2 minus 2 minus 1, it comes along the columns. This is the A. So A transpose R is this, minus 1 into R11, so that is minus R11, minus 2 into R12, it is minus 2R12. So this product is this, and this product is this, and 2 minus 1 into R12 is this, and 2 minus 1 into R12 R22 is this. So we get this as A transpose R, and we can multiply R. RA is transpose of A transpose R, so we can directly write by taking transpose of this as this. So we can determine one of the products, take its transpose to get the other matrix, and now we add them. So after adding, we get these three on the left hand side, and by comparing that to selected Q, by comparing that to that Q which was selected, I am sorry for some goof up, that Q which was selected, we equate this equal to minus 2, this 2 equal to minus 2, and this equal to 0. We get these three equations, and solving them, we get the R matrix, which comes as the identity matrix. Now I made this comment earlier, and again I am making that comment. that when we select a Q, we keep in mind that this selection should be such that this R comes a nice matrix. So for that Q which was selected, this R is coming as a identity matrix, a diagonal matrix, let me say, and which will be easier to analyze subsequently, because we have to set up Vx and we have to obtain V dot x, etc. So even though the analysis via this, the analysis of linear system, then getting the Lyapunov function equal to x transpose Rx, in which we have to substitute R and we have to proceed further to determine the region of stability of nonlinear system. This appears little straightforward, but it will be simpler if R has a nice form. If R is little complicated, then the analysis, subsequent analysis will not be simpler. So maybe that initially if we are not able to select a Q which gives a good R, we can repeat this exercise for some more values of Q, and thereby we will be probably in a position to select a good Q which results into a nice form of R, a good R, although it is not absolutely essential. But the effort we put in selection of Q gives its benefit in analysis of Vx when we are going to find out the region of stability of the nonlinear system. So x transpose Rx, this Vx is x transpose Rx, and R was identity, so we get Vx as x1 square plus x2 square, and V dot x will be 2x1 x1 dot 2x2 x2 dot, and we make substitution x1 dot by this and x2 dot, the whole term, the linear term as well as the nonlinear term. We simplify, we get this, we further simplify, get this, and finally we get this after all the simplifications. Now we have to analyze that. We have to find a K, that means radius of Vx, in which V dot will be negative. And we see that one simpler thing to say is that if x2 dot is less than 1, and so we get this condition that Vx, that K we are taking, although it is not the slightly large K would have been possible, but we safely say that this K, Vx less than equal to K, where K is 1, gives the region of stability for the nonlinear system in this example. And as I said, we have to select Q to be able to analyze this easily. Also, selection of Q will give appearance of this, and accordingly this region may come slightly different and may come closer to the actual region in which nonlinear system has stability. So selection of Q, choice of Q has again an important role, even though this indirect approach to analysis of nonlinear system is somewhat easier compared to the direct approach in which we have to select the Vx in some manner. So a Vx selected in this manner via the linear system is a simpler approach. We summarize. We have studied the Lyapunov's indirect method here with application first to linear system, and then we extended to nonlinear systems to establish the region of stability around the equilibrium or the origin. Then what we see that in case of linear system, this is a statement without proof, that the results obtained by application of Lyapunov's stability criterion are identical to those obtained by Routh-Hurwitz stability criterion. And From this lecture, these 3 lectures, of course, one was on mathematical concepts essential to learn the LYPUNOV'S stability analysis. Other one was that LYPUNOV'S direct approach. Before that, the definitions, etc. And in this one, the LYPUNOV'S indirect approach. This, if you remember everything, then we will be probably able to do stability analysis for linear as well as nonlinear system. But at least one thing we have to remember, that A transpose R plus RA equal to minus Q. This we have to remember, the stability analysis of the linear system. We will come across this very often in our subsequent chapters, maybe in the linear quadratic regulator design or in state estimation using Kalman filter. So at least one takeaway for every student should be to remember this stability analysis of linear system using LYPUNOV'S method. However, if we remember everything, considering even those extension to nonlinear system, it will be better. Another remark I want to make is that this LYPUNOV'S stability criterion remains a very complex thing to learn. So we are generally not in ease with LYPUNOV'S stability analysis method. However, competence grows with efforts and further study. So you can do further self-study. My main intention was to familiarize you with this one, which I have done. We will apply this in subsequent chapters. Thank you and see you again in another video lecture.